Hi and Assalamualaikum warahmatullahi wabarakatuh. My name is Lia Maisara. Based on the picture above, that is our poster. Our poster is based on A3 paper size and the content is, there is introduction, the content is product model cross-range and the calculation. And for the next page is discussion and conclusion. And lastly is the reference. Hi and Assalamualaikum warahmatullahi wabarakatuh. My name is Ilya Maisara binti Syam and I'm from Bmp S1 Group 2. Today, me and my friend are going to introduce our experiment, that is torsional loadings evaluation from actual structure. The product that we have been using is cross-range. Today, I will introduce what is torsional loadings. In the field of solid mechanics, torsion is the twisting of an object due to an applied torque. Torsional loading is a test that twists a material to a specified degree with a specified force or until the material fails in torsion. In sections perpendicular to the torque axis, the resultant shear stress in this section is perpendicular to the radius. Next, I will talk about our objective. What is our objective on the experiment? First is to determine the behavior of a material or test sample exhibits when twisted or under torsional force. Second, to show how to calculate the shear stress of circular shaft subjected to torsional loading. Third, to determine the equation of equilibrium, yield shear strength, ultimate shear strength, and modulus of rupture in shear. And lastly is to ensure the quality of the product and design is manufactured correctly.
Hi, my name is Lavinia. I will present about our product, which is cross-range. This is the original structure. For example, shown in the picture. Idealized model. Material we use is steel, which is 80 GPa. And here to here is length 1. It is 230 mm. And here to here is length 2. It is also 230 mm, and then we convert to meter is 0.23 meter. F1, F2. F1 and F2 is 80 Newton, but the radius is 6 mm, and then we convert to meter is 0.006 meter. The diameter is 12 mm, and convert to meter is 0.012 meter. I will show the video of cross-range operation.
I sound really fine. 아무렇지 않은 척 아무도 모르게.
Assalamualaikum and selamat sejahtera. My name is Ainur Natasha binti Azmi. I will explain about the calculation of the cross range. Okay, as you can see, I already draw the free body diagram of the part. Firstly, we find the equation of the equilibrium, which is total Fx equal to 0, total Fy equal to 0, and moment equal to 0. Okay, for the Fx equal to 0, there is no force in x-axis. For the y-axis, F1 minus F2 equal to 0. F2 is negative because we assume the force is going downward. So F1 minus 18 Newton equal to 0. Then we get F1 equal to 18 Newton. Okay, for the moment, 18 Newton multiplied by 0.23, which is the length of L1, plus 18 Newton multiplied by 0.23 meter, which is the L2, minus by T equal to 0. And T, we get 36.8 Newton per meter. Okay, then we find the shear stress, which is tau. Firstly, we find the polar moment of the inertia. So the formula is J equal to pi over 2 multiplied by R square root of 4. So the R is basically the value of radius. So pi over 2 multiplied by 0.006 square root of 4. And then we get 2.04 multiplied 10 power of negative 9 meter. And then we find the tau allowed. The formula is T multiplied by C per J. So C is the radius, T is the value that we find from the modulus, per J. J is the polar moment of the inertia. So 36.8 multiplied by 0.006 per 2.04 multiplied 10 to the power of negative 9. And then we get 108.24 megapascal. And then to find the tau max, Tc per J. T is the value of the internal. So we find the internal tau first. So 36.8, which is the value from the moment that we calculate just now, plus 0.23 the length multiplied by force, which is 80, and then we get 55.2 Newton. From then we can calculate tau max. So tau max equal to Tc per J. So T is the value that we calculate from the internal tau, which is 55.2 multiplied by 0.006 divide by 2.04 multiply 10 the power of negative 9, and then we get 162.35 megapascal. Okay, next we find the angle of twist. So the formula is TL per JG. So the T is the value from the moment, which is 36.8 multiplied by 0.23, which is the length, divide by 2.04 multiply 10 the power of negative 9 multiply 80 multiply 10 the power of 9. So we get 0.052 radian. And then we change the radian to the degree. We need to multiply 180 per pi. So we get 2.98 degree. And lastly, we find the factor of safety. So the formula is tau max per tau allowed. So 162.35 multiply 10 the power of 6 divide by 108.24 multiply 10 the power of 6, and then we get 1.500. So the project is safe in this working condition because the 1.500 is in the range of the factor of safety between 1.3 to 1.5. So the application is for use with highly reliable materials where loading and environmental conditions are not severe and where weight is an important consideration. So that's all for the calculation.
Today, I want to discuss about conclusion and discussion for this project. Let's talk about discussion. Our group chose cross wrench as our model project. Okay, in this project, we learn about torsion. What is torsion? Torsion refers to the twisting of a shaft loaded by a torque, commonly known as twisting couple or twisting moment. Okay, in this experiment, when a torque is applied to the structure, it will twist along the axis. So, the more the angle of twist, larger the shear strain. Based on calculation, we get the value for the polar moment, which is 2.04. From that, we get the value for the factor safety, which is 1.5. This is important because we want to know the shaft is safe or not. So in this project, the shaft is safe in this condition working. Because of what? Because we consider the safety in this project. Okay, finally, let's talk about conclusion. In conclusion, from this experiment, we learn about torque and torsion, as we can develop relation between the angle and the shear strain. Okay, then we are able to apply our knowledge to calculate the torque and torsions, the stress and the maximum yield stress. Finally, we are understanding of basic laboratory practice. Overall, what I can conclude, the torsion test is to determine the behavior of material or test sample XTB when faced or under torsional stress as a result of applied moment that can cause shear strain upon the